Okay, problem 2.42 is yet another one of those really mathematically intensive problems, so strap yourselves in for a very long derivation process. In problem 2.21, we were given the stationary Gaussian free particle wave packet. Now we want to solve 2.21 using a traveling Gaussian wave packet instead. Our wave function of interest is psi of x comma 0 being equal to ae to the negative ax squared, which is what the original wave function in 2.21 was, with this additional e to the ilx term behind it, where L is some real constant. We're given the hint that when we do the traditional method of a Fourier transform from phi of k to psi of x comma t, we should do a variable change to u, defined as k minus L. And we're also given part of the answer, which is we're given psi of x comma t in terms of the variable gamma, which is equal to the square root of 1 plus 2ia h bar t divided by m. And then finally, we're told that psi of x comma t has the structure of a Gaussian envelope modulating a traveling sinusoidal wave. What we mean by this is that there's two terms here, e to the I times a variable, which is a sinusoid. Remember, this can be decomposed into cosine of L x minus h bar Lt over 2m plus I sine of that same thing. So that's the sinusoid, and then we have this complex, and then we have the standard exponential, which is basically an amplitude modulation term. This is going to sort of control the amplitude of the complex exponential over here, which becomes a sinusoid. So this is just a standard, this is exactly sort of the same situation we encountered back when we were learning about this. The only difference now is that the math is a little bit more complicated because of the e to the ilx term. So let's start with part A. So 2.21a asks us to normalize this wave function. So we're trying to find, 1 is equal to the integral from negative infinity to positive infinity of magnitude psi x comma 0 squared dx. This is done in the exact same way as 2.21 was done, because note that e to the ilx, when we take the magnitude squared, just cancel out because we're multiplying e to the negative ilx. Those two cancel out to 1. So what we're going to get is that 1 is equal to a squared times the integral from negative infinity to positive infinity times e to the negative 2a x squared dx. And then we can just solve this integral as standard. So what we're going to find is that a is going to equal 2a over pi to the power of 1/4 if we solve this as a Gaussian. And at this point, what we know is then that psi x comma 0 is therefore equal to 2a over pi to the power of 1/4 times e to the negative ax squared e to the ilx. And now we are ready to begin the problem proper in part B. Okay, now starts the hard part. So in part B of 2.21, we were asked to find psi of x comma t. Now, if you remember these types of problems, the way we're supposed to solve this, we're supposed to use a Fourier transform. So the general formula is that psi of x of t can be expressed as a Fourier transform of phi of k. So we can write psi of x comma t as 1 over the square root of 2 pi times the integral from negative infinity to positive infinity times phi of k times e to the I times kx minus h bar k squared over 2m multiplied by t. And then we close this off with the dk. To find phi of k, we can do a Fourier transform from psi of x comma 0. This is going to give us 1 over square root of 2 pi times the integral from negative infinity to positive infinity of psi of x comma 0 times e to the negative ikx, this time in terms of dx. So we have to start by finding phi of k first. So to do that, we plug in our accepted value psi of x comma 0. So phi of k is then going to equal 1 over the square root of 2 pi times the integral from negative infinity to positive infinity. Substituting psi of x comma 0 in, we have 2a over pi to the power of 1/4 e to the negative ax squared e to the ilx e to the negative ikx dx. So at this point, we can combine exponentials and also move the constants out. So we have 1 over the square root of 2 pi multiplied by 2a over pi to the power of 1/4 And then we have the integral from negative infinity to positive infinity of e to the, let's see, negative ax squared plus ilx minus ilx. So let's rewrite this as plus il minus il multiplied by x. And from here, this doesn't seem like a very easy integral to solve. However, if you go back to problem 2.21, we actually get a hint. And the hint that we get in that problem is that integrals of this form, from negative infinity to infinity, of e to the negative ax squared plus bx dx, can be handled by doing something called completing the square, where we let y equal the square root of a times x plus b over 2a, and then redefine ax squared plus bx as equal to y squared minus b squared over 4a. And from that point, if we do a change of variables to y, then we get that dy is going to equal, from here, the square root of a times dx. So we can do a change of variables to dy, and this goes from, being an integral of an exponential of a secondary polynomial to an integral of an exponential of just, a variable squared. This term in the exponential is going to come out as a constant. Makes our job infinitely easier. So let's redefine the integral this way. So if we redefine our integral, phi of k, to equal, this is going to be 1 over the square root of 2 pi multiplied by 2a over pi to the power of 1/4. And then we have our integral from negative infinity to infinity. And let's try to match this form. So e to the negative ax squared plus bx dx, where in this case, a is just going to equal a, and b is going to equal, let's see, I times, and you know what, I just realized I made a bit of a error up here. It's il minus ik. My apologies. So at this point, b is going to equal the negative of this. So this is b is going to be equal to I times k minus l instead. And then at this point, then we redefine y. So y is going to equal the square root of a times x plus b over 2a. dy is going to equal square root of a times dx. Therefore, ax squared plus a bx is going to equal y squared minus b squared over 4a. So what that means is that we can rewrite phi of k to equal 1 over square root of 2 pi times 2a over pi to the power of 1/4 multiplied by our integral from negative infinity to positive infinity. And we're going to rewrite this e to the negative of y squared minus b squared over 4a dx. We can then, split this into two exponentials. The one e to the positive b squared over 4a just moves out because it's a constant. So this is going to equal 1 over the square root of 2 pi times 2a over pi to the power of 1/4 multiplied by e to the power of b squared over 4a, because that just moves out of our integral from negative infinity to positive infinity, e to the negative y squared dx. And we want to change that to dy, so we're going to do dy times the square root of a. So let's see, let's assign a little bit. So this is going to equal, so we have square root of a over 2 pi multiplied by 2a over pi to the power of 1/4 multiplied by the exponential of b squared. Let's see, b squared is going to give us negative k minus l squared. So yeah, negative k minus l squared divided by a is just a, so 4a times the integral from negative infinity to positive infinity, e to the negative y squared dy. And at this point, this is just the standard Gaussian integral, so we can solve this very trivially. If you don't remember how to do Gaussian integrals, I would heavily recommend you go back. I think one of the first problems in this book talks about how to actually, or the actual derivation for solving a Gaussian integral. So you can go there and do that. But at this point, you should basically have this type of integral memorized, hopefully. This is just going to equal the square root of pi. So we're going to get, so the square root of pi, this is going to cancel out with the pi down here. We get square root of a over 2 times 2a over pi to the power of 1/4 times e to the negative k minus l squared divided by 4a. And we have v of k. Our next job is we want to transform this into psi of x comma t via the Fourier transform a second time. Okay, quick correction. Apologies in advance. I just realized I made a bit of a mathematical error here. Going from dx to dy, we know that dy is equal to the square root of a dx, so that means dx is actually equal to dy times the square root of a, over the square root of a. So I made a bit of a mistake here. This is supposed to be 1 over the square root of a. So in that case, what we get is that this is going to equal, let's see, 1 over 2 pi a. So the square root of pi cancels out as before. We have 1 square root of 1 over the square root of 2a. So actually, I'm going to rewrite this a little bit more. We can rewrite this as 1 over 2a pi to the power of 1/4, because we have 2a to the 1/4 and then 2a to the 1/2 at the bottom. 1/4 minus 1/2 is negative 1/4. And then we have e to the negative k minus l squared over 4a. So yeah, that actually looks more correct. Apologies for that. Bit of a mathematical error. Okay, now the second and harder part, which is that we now have to transform into psi of x comma t. Let's start off by taking the hint, which is that we want to change variables to u equals k minus l. So if we do that, if I say that u is equal to k minus l, recognize that psi of x comma t is a dk integral, so I'm going to want to convert du to dk. Well, in this case, l is a constant, so du just equals dk. K itself is going to equal u plus l, and this phi term is going to equal 1 over 2 pi a to the power of 1/4 e to the negative u squared over 4a. So now let's write psi of x comma t via the transformation. This is going to be 1 over square root of 2 pi times the integral from negative infinity to positive infinity of, first off, phi of k. So 1 over 2 pi a to the power of 1/4 e to the negative u squared over 4a. And let's see, then we have this horrible exponential, e to the ikx minus I h bar k squared over 2m multiplied by t dk. So let's change variables into u. So I'm going to start by moving out the constants. 2 pi 1 over 2 pi a to the power of 1/4. And then our integral from negative infinity to infinity, e to the negative u squared over 4a, e to the u plus l, minus I h bar t over 2m, u plus l squared, moving to du. And this is not a fun thing, so I'm going to condense all the constants here to a for now. Integral from negative infinity to infinity. I'm going to write this out as an exp form, just to make it easier on my hand. Negative u squared over 4a, let's see, plus iku plus ixu plus ixl minus I h bar t over 2m times u squared plus 2ul plus l squared. This time close it off with a du. Immediately I see ixl has no u term in it, that's just a constant, so this is going to be a e to the ixl, integral from negative infinity to infinity exp, negative u squared over 4a plus ixu minus I h bar t over 2m u squared minus I h bar lt over m times u, I believe. I h bar t over 2m, 2's cancel out. U goes at the front, L goes at the front top, yeah. And then minus I h bar L squared t over 2m. Close this off with du. Immediately I can also move this term over. Negative I h bar L squared t over 2m. Yeah, I can move this term over because it has no u dependency on it. This is going to give me a e to the I x l minus I h bar l squared over 2m times t. And then our integral from negative infinity to infinity of e xp to the, and I'm going to rearrange the terms a little bit, negative u squared over 4a minus I h bar t over 2m times u squared. And then plus I x u minus I h bar l t over m times u. Close this with a du. And from here, I can do a bit of distribution. So I'm going to start by getting the a constants back in. So 1 over square root of 2 pi times 1 over 2 pi a to the power of 1/4. Is that, let me just verify that's correct. Yeah. And then times our exponential e to the I x l minus I h bar l squared over 2m times t times our integral from negative infinity to positive infinity of e to the power of, let's see, u squared negative 1 over 4a minus I h bar t over 2m plus u times I x minus I h bar l t over m. And I'm going to close this off with a du. So remember, once again, we're trying to get this into the form of the hint from earlier. So remember, we want to get this into the form of e to the negative a u squared plus bu. So to do that, and you know what, let's actually do this in purple. So I'm going to bring the hint down from earlier, and I'm going to write it in purple. So the integral from negative infinity to positive infinity of e to the negative ax squared plus bx can be, dx can be rewritten in terms of y, and we can rewrite this as the integral from negative infinity to infinity of e to the negative y squared plus b squared over 4a, where y is equal to the square root of a times x plus b over 2a. So we want to rewrite this integral this way, in which case, let's do it in blue. I can rewrite the integral as the integral from negative infinity to positive infinity of e to the, let's see, negative. So I'm going to factor out a negative 1, and I'm going to get 1 over 4a plus I h bar t over 2m times u squared. And I factor out a negative 1, but I want the second term to be positive, so plus I h bar l t over m minus I x multiplied by u. Close it off with a du, because in this case, let's see. Yeah, and then so y equals, so dy is going to equal square root of a times dx. So dx is going to be equal to dy over square root of a. So if we switch this, then this is going to give us the integral from negative infinity to positive infinity e to negative y squared plus b squared over 4a dy times 1 over square root of a, where a is equal to 1 over 4a plus I h bar t over 2m, and b is equal to I times h bar l t over m minus x. Forgive the double use of a here. I'm going to try my best to write the a's on the left, which are just equal to a in green. I'm going to try to write the a's which are included here, which equal these more complex things in blue. So in that case, psi of x comma t is going to equal everything at the front here and then the blue expression. So 1 over root a integral from negative infinity to infinity e to the negative y squared plus b squared over 4a. Close it off with a dy. Let's see, we can move some stuff out. So this is going to be converting everything, we're going to get 1 over square root of 2 pi times 1 over 2 pi a to the power of 1/4 times 1 over the square root of 1 over 4a plus I h bar t over 2m multiplied by e to the I x l minus I h bar l squared over 2m times t times e to the b squared over 4a, which is going to be negative h bar lt over m minus x squared over 4a, which is going to be 1 over a plus 2i h bar t over m. And then integrated from negative infinity to infinity, e to the negative y squared dy. So this is just root pi. So the root pi at the top cancels out with the root pi at the bottom here. And then also, if you look back up, we're trying to redefine this in terms of gamma. So let's see what we can do. So we know that we have this variable gamma, which is going to equal, I just forgot it, the square root of 1 plus 2i a h bar t over m. So let's see if we can move some stuff in terms of gamma. Immediately, I see here that I can remodel this. So let's rewrite psi. So psi of x of comma t is going to equal 1 over square root of 2 times 1 over 2 pi a to the power of 1/4. And I'm going to multiply everything here by square root of 4a over square root of 4a. So we're going to get square root of 4a divided by, and if I multiply square root of 4a onto the bottom, let's see, that's going to give me the square root of 1 plus 2ia h bar t over m. And then we have e to the I x l minus I h bar l squared over 2m times t times e to the negative h bar lt over m minus x squared. And you know what? This bottom term looks like it can actually get turned into a gamma as well. If I multiply by a over a, then I'm going to get a at the top. At the bottom, I'm going to get 1 plus 2ia h bar t over m. So let's see. This is going to give me 2 at the top, which is going to cancel out with the root 2. Yeah, so 1 over 2 pi a to the power of 1/4 times the square root of 2a over gamma times e to the I x l minus I h bar l squared over 2m times t e to the negative h bar l t over m minus x squared multiplied by a, and at the bottom this is just going to be gamma squared. So let's see, e to the negative a x minus, e to the, okay, and then let's cancel this out a little bit more. So we have 2a to the 1/2 at the top and 2a to the 1/4 at the bottom. That's going to make 2a to the 1/4. So this is going to be, let's see, 2a over pi to the power of 1/4. And then we have 1 over gamma. And then let's move the gammas at the front. So this is going to be e to the negative a. And I'm trying to match this to the hint. So in the hint, we have x minus h bar lt over m squared. But recognize, there's no difference really, because of the square term, we can just add a negative at the front without any problems. Because if we look at it, this is actually equal to, let's see, negative 1 multiplied by x minus h bar lt over m. And if we're squaring this, in that case, well, the negative 1 squared just becomes positive 1 again. So this is actually exactly the same as the top term with everything reversed. So we can rewrite it this way. Then we divide by gamma squared, and then we have e to the, let's see, we can pull out an il. So il multiplied by x minus h bar l over 2m times t. And if I copy paste the top term here and see if I can match it, 2a over pi to the 1/4, 1 over gamma, e to the negative a x minus h bar lt over m squared divided by gamma squared, e to the il x minus h bar lt over 2m. So we do match, and we thankfully are done with part B. Okay, so there's an extra part here. Notice that psi of x comma t has the structure of a Gaussian envelope, modulating a traveling sinusoid. So we've gone over this already. The complex exponential is the traveling sinusoid, and then this exponential over here, which is real, is the modulating term. We want to know two things: the speed of the envelope and the speed of the traveling wave. So let's start with the speed of the traveling wave, because the traveling wave is defined using this complex exponential. Recognize that traveling waves move according to the formula of k times x plus minus vt. And that's exactly what we have here. So the k here is replaced with an L, and then we have x minus v times t, where v is apparently equal to h bar L over 2m. In contrast, according to what we learned in 2.4, the envelope travels at twice the speed of the phase velocity. So v of the envelope is equal to twice the phase velocity, which is going to be equal to h bar L over m. So if you don't remember this, we went over it when we were talking about, I believe, free particles. Let me just double check to make sure I'm not lying. So it should be in chapter 2.4, if I'm correct. Yeah, so in chapter 2.4, when we talked about the free particle, we talked about the speed, and one of the things we mentioned was the distinction between the envelope speed and the phase speed. We just found the phase speed, aka the speed of the traveling sinusoid, via just the standard formula k times x plus minus vt, and then we proved in that chapter, 2.4, that the group velocity, aka the speed of the envelope, which is this traveling Gaussian term right here, travels at twice the speed of the phase velocity, so therefore we just multiply by 2 and get h bar L over m. So this is pretty trivial. Okay, moving on to part C, we now want to find the magnitude squared of the wave function. So to do this, we're going to look at psi of x comma t, which we found in part B. First thing we can realize is that there's a complex exponential here, e to the il times a bunch of crap. This automatically just gets canceled to 1, because if you multiply by the complex conjugate, it's going to get multiplied by e to the negative il of all the same crap, and those two cancel out to 1. Other than that, the other term that has a complex value in it is going to be gamma. So if we know that gamma is going to equal the square root of 1 plus 2ia h bar t over m, and we also know that gamma star is going to equal the square root of 1 minus 2ia h bar t over m, then we know that the product gamma gamma star is going to be just the square root of the multiplication of these two complex conjugates, which we already know the result of. It's just going to be a squared plus b squared, 1 plus 4a squared h bar squared t squared over m squared. So now let's write this out. The magnitude of psi x comma t squared is going to equal, so we have 2a over pi to the 1/4 squared, which is going to give us square root of 2a over pi. Then we have 1 over gamma gamma star. Then we have e to the negative a x minus h bar lt divided by m squared divided by gamma squared. And then we have e to the negative a x minus h bar lt divided by m squared over gamma star squared. Let me just double check that that's correct. Negative a x minus h bar lt over m squared over gamma star. Yeah. Okay, now let's write everything out fully. This is going to be the square root of 2a over pi multiplied by 1 over the square root of 1 plus, let's write this as 2a h bar t over m squared. And then we're multiplying by e to the, and this is going to be, let's see, negative a x minus h bar lt over m, whole thing squared, multiplied by 1 over gamma squared plus 1 over gamma star squared, like that. And then now we can do a little bit of manipulation, because in the original problem for this, we wanted to express the answer in terms of what's called omega, where we defined omega as this new variable, omega equaling the square root of a divided by 1 plus 2h bar at over m squared. So in that case, we have the denominator here. We have a square root of a up here. We can move that over, and what we're going to get is that the magnitude of psi squared is then going to equal the square root of 2 over pi multiplied by omega times, I'm going to write this as an exp to make this easier on my hands, negative a x minus h bar lt over m squared multiplied by gamma star squared plus gamma squared over gamma squared gamma star squared. And at this point, we know what gamma gamma star is. If we take the squared of gamma gamma star, that's just going to be gamma squared gamma star squared. So this is going to give us the square root of 2 over pi times omega times exp negative a x minus h bar lt over m squared, and then multiplied by, at the top we have gamma star squared, which is going to be 1 minus 2ia h bar t divided by m. Is that correct? 1 minus 2ia h bar t over m. Yeah, and then plus 1 plus 2ia h bar t over m. And then at the bottom we have 1 plus 2a h bar t over m squared. And then we cap off this entire thing. These two terms automatically cancel out. We get square root of 2 over pi times omega times exp times, and I'm going to move the a over because this is looking very similar to an omega term. And I'm going to move the 2 here out, so this is going to be negative 2 x minus h bar lt over m squared, and then we have the a at the top over 1 plus 2a h bar t over m squared. If we look at what omega equals, this is just omega squared then, so we can rewrite this finally as the square root of 2 over pi times omega times e to the power of negative 2 x minus h bar lt over m squared omega squared. And with that, we are done with part C. And now we arrive to part D, which is sort of our old nemesis in these kinds of problems, which is finding the expectation values of x, x squared, p, and p squared, along with their respective uncertainties. Conceptually, a very simple thing to set up. However, the integrals tend to be excessively difficult. Honestly, at this point, assuming that you're actually comfortable with everything, it wouldn't be too bad to just plug the resulting equations into a calculator and solving them that way. That being said, I am going to do them by hand because I hate myself, and also they are somewhat good mathematical practice. So let's begin with the expectation value of x. So this is just going to equal the integral from negative infinity to infinity of x psi star. The x, I've written out the x-dependent or time-independent solutions because the time-dependent function e to the il is going to cancel out to just 1 when we multiply it by its complex conjugate anyway. So this is going to give us the integral from negative infinity to infinity. We start off with the constants at the front, so this is going to become square root 2a over pi multiplied by 1 over gamma times gamma star. And then we have x times e to the negative a x minus h bar lt over m squared times 1 over gamma squared plus 1 over gamma star squared dx. This is going to give us, move the square root 2a over pi out. Gamma times gamma star is going to give us 1 over 1 plus 2a h bar t over m squared. Take the square root of everything here. And then we have our integral from negative infinity to positive infinity of x times e to the negative a x minus h bar lt over m squared times, I believe this is going to end up equaling 2 as we solved at the top, and at the bottom it's going to be just 1 plus 2a h bar t over m squared. Close this off with a dx. And this is not a very fun integral to actually do. Immediately I see here that we have an x minus h bar lt over m term. So let's see. Realistically, if I wanted to, I could try solving this using the hint that we had from way earlier on, which is that we could solve integrals of the form of ax squared plus bx by completing the square, but I really don't want to do that if I don't have to. So let's see if I can make this a little bit easier on myself. First off, I'm going to incorporate omega into this once again. Because omega is just going to be a constant. So this is going to be the square root of 2 over pi times omega times the integral from negative infinity to positive infinity of x e to the negative 2 omega squared times x minus h bar lt over m squared dx. Let me just double check that that's actually correct. Negative 2x, negative 2 omega squared x minus h bar lt over m squared. Yeah. Okay, so at this point, let's see. I might be able to do a variable substitution, but there is a time dependency here. So no, it looks like I won't be able to do a variable substitution. I'm just going to have to straight up use the really painful method of completing the square. So if I expand this out fully, this is going to give me square root of 2 over pi times omega times the integral from negative infinity to infinity, x e to the negative 2 omega squared multiplied by x squared, let's see, minus 2x h bar lt over m plus h bar lt over m squared dx. I can move out some constants here. So let's see. Yeah, I can move out square root 2 pi omega, and I can move out an exponential e to the negative 2 omega squared times h bar lt over m squared times the integral from negative infinity to infinity of x times e to the negative 2 omega squared x squared plus 4 omega squared h bar lt over m times x. Is that correct? 2 omega, negative 2 omega squared x squared plus 4 omega squared h bar ltm x dx. Yeah, and then let's rewrite this side. Square root 2 over pi times omega e to the negative 2 omega h bar lt over m squared. And then this same integral, negative infinity to infinity, x e to the negative 2 omega squared x squared plus 4 omega squared h bar lt over m multiplied by x dx. And I will be right back as soon as I look up the complete the square solution. Okay, right. So the complete the square solution says that we want to change this form into negative ax squared plus bx. So let's do that. And you know what? For now, I'm going to work purely with this integral. So it's going to be the integral from negative infinity to positive infinity, x e to the, and I'm going to move the negative out, and this is going to give me 2 omega squared x squared minus or plus negative 4 omega squared h bar lt over m multiplied by x. And I'm going to close this off with a bracket instead of parentheses. So if we do it this way, then a is going to equal 2 omega squared b is going to equal negative 4 omega squared h bar lt over m. Let's see. At this point, we can redefine a new variable. We can define y. Y is going to equal the square root of a times x plus b over 2a. So that means, let's see. Yeah, so we can rewrite this now as the integral from negative infinity to positive infinity of x times e to the negative y squared plus b squared over 4a dx. So we want to switch from dx to dy, so dy is going to equal square root of a dx, or dx is going to equal dy over square root of a. Also, from this, what this tells us is that we can switch to y as well from here. So this is going to be x is equal to y over square root of a minus b over 2a. So this is going to equal negative infinity to positive infinity of y over square root of a minus b over 2a times 1 over square root of a times e to the negative y squared. And then I'm going to move the e to the b squared over 4a out, and then we have dy. Not fun. This is not fun. This looks disgusting. So from this point, the expectation value of x is going to equal square root of 2 over pi times omega times e to the negative 2 times omega, let's see, omega h bar lt over m. Take the square of this, and then we do the integral here, which is going to come out as e to the b squared over 4a times 1 over the square root of a times the integral from negative infinity to positive infinity of y over square root of a e to the negative y squared minus b over 2a e to the negative y squared dy. So then we have to split this up again into two different integrals. So this is going to give us square root of 2 over pi omega e to the negative 2 omega h bar lt over m squared. And then we have in red e to the b squared over 4a times 1 over root a, and then multiplied by 1 over square root of a times the integral from negative infinity to infinity of y e to the negative y squared dy, subtracted by b over 2a integral from negative infinity to infinity of e to the negative y squared dy. So this term right here is just square root of pi because it's a Gaussian. This term we're going to have to use u sub. So this is going to give us, see it's in green, u is equal to y, du is equal to dy, dv is equal to e to the negative y squared, dy, v is equal to no, I'm doing this wrong. Sorry, give me one moment. Okay. I mixed up my techniques. You're not supposed to use u sub here. You're supposed to take advantage of the fact that this is a derivative term. So if we look, if we say, okay, d by dy of e to the negative y squared is going to equal, negative 2y e to the negative y squared dy. So that means that y times e to the negative y squared dy is actually equal to d by dy of e to the negative y squared multiplied by a negative at the front and then 1/2. So we can rewrite this as square root of 2 over pi omega e to the negative 2 times omega h bar lt over m squared e to the b squared over 4a times 1 over square root of a. You know, I should write this in red to emphasize that there are still variables here that we don't know about. E to the b squared over 4a times 1 over square root of a, and then 1 over square root of a times the integral from negative infinity to positive infinity of, add the negative at the front, and then add the 2 at the bottom, so we get d by dy of e to the negative y squared dy, and then minus b root pi over 2a. And, excuse me, at this point, this integral just cancels out. So this is going to give us, you know, e to the negative y squared evaluated from negative infinity to positive infinity, which is just going to give us, at this point, 0. So this entire thing cancels out to nothing. And what we're left with is square root of 2 over pi times omega times e to the negative 2 omega h bar lt over m squared e to the b squared over 4a times 1 over square root of a, and then we add a negative at the front, and I keep on forgetting to rewrite this in red. My apologies. We have e to the b squared over 4a times 1 over square root of a. The negative's already at the front, so we just multiply by b times square root of pi over 2a. So let's see, there's a bit of cancellation we can do. Immediately the square root of pi cancels out with the square root of pi down here. Let's also bring down the definitions of a and b. And I need to edit my properties. Give me one sec, because I am my canvas is a little bit too small. Let's make this like 10,000. There we go. So at this point, if we wanted to rewrite everything in terms of their proper definitions, we have negative root 2 times omega e to the negative 2 omega h bar lt over m squared times e to the power of b squared, which is going to give us 16 omega to the 4th h bar lt over m squared, and then divided by 4a, which is going to give us 8 omega squared. Yeah, 8 omega squared. And then we have 1 over the square root of 2 omega squared, which is going to be omega root 2. And then we have b over 2a, which is going to be negative. Yeah, okay, so the negatives cancel out automatically. So this is going to give us 4 omega squared h bar lt over m over 2a 4 omega squared. So let's see. There's a bunch of cancellation that happens. 4 omega squared, 4 omega squared, root 2, root 2. This is going to leave us with, this bottom term is going to cancel out with the top, leading 2 omega squared times h bar lt over m squared. So these two terms cancel out to 1. What we're left with is the omegas also cancel out. So actually almost everything cancels out. What we're left with is h bar lt over m. And if I look at what the actual correct solution is supposed to be, I believe that does match. H bar lt over m. Yes, okay, this is correct. So very painful process of doing this. X squared is going to be even worse, but honestly it's more of the same thing. Really, everything's pretty much the same up until sort of this point, where you're going to have to redefine x squared. So you have to redefine x in terms of y, and then square this term. And then what's going to happen is that it's going to go out again. It's basically, it's going to expand itself into, you know, the square of y over root a minus b over 2a. And the only thing that's going to change is you're going to get more terms here in this calculation down here. I really don't think it's worth it to do x squared, because it's just a more complicated version of doing the same thing we do in x. The only difference is, you're going to have three terms here. It's going to be like a y squared term, a y term, and then like a term that's just e to the negative y squared. The y squared term, to simplify it, we use this same method just multiple times and cycle through it. Earlier problems have addressed how to do this. If you don't know how to do it, you can search up how to solve integrals where you have a Gaussian multiplied by some power of x, or in this case y. I believe Wikipedia does a pretty good job of deriving it. Alternatively, just go on a calculator, go on like an integral calculator, look at the steps that they do, because those calculators typically are also pretty good at teaching you how to do these results. Regardless, the expectation value of x squared, I just don't believe it's worth it to do this. It's going to equal m squared plus 4 h bar squared a squared t squared over 4m squared a plus h bar squared l squared t squared over m squared. So yeah, just from looking at this, I really don't think I have the patience of spending the next hour trying to solve this out. The uncertainty in x is then going to equal the square root of the expectation value of x squared minus the expectation value of x itself squared. This is going to give us the square root of m squared plus 4 h bar squared a squared t squared over 4m squared a plus h bar squared l squared t squared over m squared, subtracted by h bar lt over m squared so at this point, these two terms just cancel out. What we're left with is the square root of m squared plus 4 h bar squared a squared t squared over 4 m squared a. And that is our expectation, or that's the deviation in x. Now, for p, we can make our work a little bit easier in that instead of doing the same complicated integrals for the expectation value of the momentum, we can use Ehrenfest's theorem, which we solved for way back in chapter 1. It basically says that the expectation value of p can be solved if we know the expectation value of x as the derivative of the expectation value of x with respect to time. We have the expectation value of x, h bar lt over m, so this is going to be equal to m d by dt h bar lt over m, which is therefore just going to equal m times h bar l over m, which is therefore equal to h bar l. At this point, we're going to have to, unfortunately, we can't do the same thing for p squared. So for p squared, we are going to have to calculate it manually. Once again, a very painful expression. So let's do that next. Okay, this horrible integral is going to require us to take the second derivative of the wave function. So let's see. d psi by dx is going to give us 2a over pi to the power of 1/4, 1 over gamma, and then e to the negative a x minus h bar lt over m squared over gamma squared. And then we have to bring down everything. So negative a over gamma squared multiplied by 2 x minus h bar lt over m. Yeah, something like this. So at this point, if I want to make this a little bit neater on myself, we have to move some stuff over. 2a over pi to the power of 1/4, negative at the front, a over gamma cubed, x e to the negative a x minus h bar lt over m squared over gamma squared, minus, what is that going to be, h bar lt over m e to the negative a x minus h bar lt over m squared over gamma squared. Something like that. Right. I'm looking at this, and I've ultimately decided that this just isn't worth actually going through and solving the entire way, considering that we have two terms here. One of them, we have to derive this a second time after this and get probably like 3 or 4 terms out of this, and then we have to shove that back into the integral. this just is not worth it. Once again, this is physics. We don't want to focus on math. This is way too painful to do. So I'm just going to write the answer down. If you plug this into a calculator, you should get that the expectation value of p squared is equal to h bar squared times a plus l squared. So at this point, in that case, the standard deviation in p is going to be the square root of the expectation value of p squared subtracted by the expectation value of p itself squared. This is going to equal, from expectation value of p squared, we have h bar squared a plus l squared, and then for the expectation value of p, we have h bar squared l squared. So we move the h bar out, we have square root of a plus 2l squared. Or sorry, this is a subtraction term, so the 2l the 2l squares is canceled out, and we just get h square root of a. So then, in part E, we want to verify the uncertainty principle. So the product of the standard deviations in x and p are going to give us, so if we look up above, we have the standard deviation in x, and then we want to multiply by h bar times the square root of a. The square roots of a cancel. This is going to give us h bar square root m squared plus 4 h bar squared a squared t squared over 4 m squared. So let's see, we can factor out a little bit of stuff here. For one, we can, let's see. Yeah, okay, yeah, we can use distributive, and let's say we can make this 1 over 4 plus h bar squared a squared t squared over m squared. So in that case, if I distribute out another 1 over 4 here, then I can get an h bar over 2 times the square root of 1 plus, at the top is going to be 4 h bar squared a squared t squared over m squared. So this is indeed greater than the minimum value of h bar over 2, because at this point, t starts at 0 and only gets larger over time. So because of that, the uncertainty principle is satisfied. And actually, we can also get some extra information out from this, because what we see here is that as over time t, as t gets larger, the uncertainty product gets larger and larger. So the product of the uncertainty in x and the product and the uncertainty in p actually becomes larger and gradually goes out to infinity as time goes to infinity. What that tells us is that the wave function is getting more and more spread out over time. And that's exactly the same behavior that we actually observed in the previous problem without the e to the ILX term. Back in problem 2.21, one of the things we had to do after finding the magnitude squared of the wave function was to plot out what the wave function looked like with respect to time. And what we found was that the wave function started off, with a very high peak. It started off, looking something like this. But over time, it would gradually, at some time greater than 0, it sort of starts to spread out. And as time goes to infinity, it starts looking just like a straight line. What this tells us is that even with that e to the ILX term added, sort of this behavior still is the exact same. So the wave function starts off looking like a bell curve, and over time it just gets wider and wider until eventually it flattens out into a straight line at t equals to infinity. So that's very nice. That it's just a nice thing to realize that even though we've added this e to the ILX term to represent a traveling wave, even though it's moving, it still behaves sort of in the same way as the stationary wave. And that's something that we expect, because all the e to the ILX term does really is it's adding on this extra movement factor, but the rate at which the wave function is moving forward shouldn't really affect how itself behaves. So even though the wave function has this e to the ILX term to sort of define the fact that it's moving forward, the actual behavior of the wave function itself, defined via a e to the negative ax squared, that doesn't change, and that's very comforting to know that it behaves the exact same way, because that's sort of what we expect, and if it didn't, there would be cause for a bit of concern.